All right, so hello everyone, happy Thursday. Um, Before we get started with our lecture today, I just wanted to have a reminder. I'm still out of town, and won't be back tomorrow for my office hour. So I won't be holding my office hour tomorrow. If you have any questions, email me. I might be a little bit delayed getting back to you, but hopefully I should be able to do that, after tomorrow. Today we're going to talk about performance metrics for classification. This hopefully kind of closes our discussion on classification almost. There is one model that I'm going to be talking about hopefully next Tuesday, and that's tree diagrams, tree models. But I didn't really bring it under classification, despite the fact that they can offer classification. That's because tree models are a little bit more generic. They can do regression, they can do classification. So we're going to talk about those separately. So up until now, we have talked about a variety of classifier models. We have looked into probabilistic models. We have seen k-nearest neighbors, k-nearest exemplars. We have seen what we expect from a classifier, but now it's time to discuss how we quantify the performance of a classifier, what performance metrics we use. One of the most common performance metrics is whether data instances are classified correctly or incorrectly. So what we do is we go over the number of data instances during our testing. Let's say we have n data instances, and we count how many of them are misclassified. That's going to be misclassification error. Essentially, if the class is labeled correctly, so estimated value is the same as the correct value, I'm going to assign a 0. If it is incorrectly assigned, I'm going to assign a 1, and then I count the number of ones. That indicates the number of data instances that are misclassified. That's kind of the most high-level way you can think about quantifying the performance of a classifier. However, a much more common technique is to use what is known as a confusion matrix, or it comes with different names, contingency table or error matrix. And a lot of times these names appear because the same concept is used in different domains. So confusion matrix is typically comes from data science, machine learning lingo, whereas in statistics, we often look at it as contingency table, but all of them kind of try to look at it the same way. The idea is this. Imagine I have data instances that either belong to class 1 or class 2. Now, in this terminology, in order to identify it, we define the notion of an event. Event is something of interest. Event is someone is creditworthy or not creditworthy. Event is someone is going to file a claim or not file a claim. Event is someone has a disease or not a disease. It doesn't necessarily have to be interesting. It's just whatever you're interested in. Now, for this table, we consider event to be positive and non-event to be negative. Again, it's just a notation. So what we do is we make a comparison between actual classes and predicted classes. If the actual class of a data instance is positive, that means it is an event, and it is identified as positive, we call it true positive. If the actual class is positive but is identified as negative, we call it false negative. On the other hand, if the actual class is negative, that means the data instance represents a non-event and it's correctly identified as a non-event, we call it true negative. If it's incorrectly identified as an event, we call it false positive. This basically identifies how the classifier operates based on detecting events and non-events. Now, in order to kind of assign metrics, we look at the true positive rate as sensitivity and true negative rate as specificity. What is it that we expect from a good model? Essentially, a good classifier, you want it to be able to correctly identify events and non-events. So if it correctly identifies events, that means true positive rate is high. Going back here, true positives are a lot higher than false negatives. We call this classifier to be sensitive. On the other hand, we would like it to correctly detect non-events. That means the true negative rate would be high. So going back to this table here, true negative is high, false positive is low. We call this specificity, or we want the classifier to be specific. Here's the problem. If we want to improve one of these categories, the other category most likely is going to worsen. Imagine, I'll give you an example. Let's say I have a classifier that is used in an email service. And its job is to, whenever an email comes in, it has to detect whether it's spam or not spam. So in this case, let's say event is the incoming email is spam. If you choose a different threshold, different uh, like a level for detecting event versus non-events, you're going to get either high sensitivity or low sensitivity. Example, realistic spam detectors are obviously very complicated, but let's come up with like a very simplistic example. Let's say this spam detector, this spam classifier, looks at the number of typos. So it goes through the email, and if it has like more than so many number of typos, it says this is a spam. If it's less than some number of typos, it says it's not a spam. Imagine you want to detect, to be more sensitive. That means detect more of these spam emails as spam. So what you can do is you can lower the threshold, and you can say, hey, you know what? As long as you have two typos in the email, I identify it as spam. This obviously makes it more sensitive, meaning that every spam email coming in, chances are that it's going to be detected as spam. However, it negatively impacts specificity because a lot of legitimate emails might come in and they have two typos, which is quite normal in an email. And yet your system, your classifier identifies it as a spam incorrectly. That's a false positive rate. So when you change that threshold, you can improve one, but typically you worsen the other one, which means in a lot of situations, you have to determine what is more important to you. Sometimes detecting what is more important is kind of easy. For instance, that example of spam detector, spam classifier. What is more important? If you miss spam emails, if you miss to identify them as events, quote unquote, what's going to happen is a spam email is going to come to the user's inbox, and the user has to manually delete it or identify it as spam. That's obviously annoying, but it's not the end of the world. But imagine you make it more sensitive, right? By detecting more and more emails, even incorrectly as spam, what's going to happen is some legitimate email is now going to be identified as spam, which could have very significant ramifications. You may miss a very important email just because it had two or three or 10 typos in it, right? So in this example, for instance, if I say event, event means email is spam, most likely specificity is going to be more important. You're willing to risk receiving some spam emails and identify it as non-events because you don't want to risk losing or missing any of the emails that are actually non-spam. In certain other situations, however, determining which one is more important is not really straightforward. Imagine you have a roommate, and imagine there's COVID, and there is a test to detect whether people have COVID or not. From the perspective of your roommate, sensitivity or specificity is more important. Your roommate wants to make sure that if I don't have COVID, this test doesn't incorrectly assume that I have. In this example, I'm assuming event means the person has COVID. Why? Because if it says I have COVID, then I have to, quarantine and, isolate and all that stuff, which I don't want to do. From your perspective, though, you don't want to take any risks. So your preference would actually be that this test is more sensitive. So from your perspective, even if your roommate does not have COVID, actually, you're okay with him or her being identified as having COVID because um, he or she having to isolate, for example, is not going to impact you. What you don't want to happen is the opposite, that your roommate has COVID, but this test fails to identify it. It gives a false negative to it. So in a lot of different situations, and this becomes important because when you're training your classifier, sometimes you have to decide whether you want to penalize lack of sensitivity or lack of specificity. And you have to kind of go back to the application to see which one is more important. Using that confusion matrix, a lot of additional metrics can be defined. This is a list of relatively exhaustive list of metrics that we can define. Obviously, one important one is classification accuracy, which is true positives plus true negatives divided by all positives and all negatives. Remember, some of the positives are correctly identified as positive, some are incorrectly identified as negative. So P would be true positive plus false negative. Likewise, N would be true negative plus false positive. Opposite of that is going to be classification error. False positives plus false negatives divided by the total positives, total negatives. Sensitivity, as I mentioned, and again, it comes with different names that have originated from different domains. It might be called recall or true positive rate. That's the true positives divided by the total positives. What percentage of total positives I identified as positive correctly? We have precision, which is true positives divided by any data instance that I identified as positive, either true or false. Specificity or true negative rate is true negatives divided by total negatives. We also have kind of the dual of precision would be negative predictive value, which is true negatives divided by any data instance identified as negative, either true negative or false negative. We also have fallouts, which is false positives divided by true negatives. So what percentage of, I'm sorry, overall negatives. So what percentage of overall negatives is incorrectly identified as positive? Dual of that is going to be miss rate, how many positives you miss by identifying them as false negative. And then we have F1 score, which is a combination of precision and recall. Essentially, like I said, for any application that you have, you're going to have to see which one has more of an impact or negative impact on your application of interest. And based on that, you try to train your classifier so that it optimizes that particular metric. One thing important about both sensitivity, which is true positive rate, or specificity, which is true negative rate, is that both of them are conditional. If you go back here, you notice that true positive rate is true positives divided by total positives, or true negatives for specificity divided by total negatives. It's conditioned upon the total number of positives or the total number of negatives. This is not always the best approach. We talked about that. We had that exercise in our Tuesday's class when you had a disease that was rare. You see that if you have an event which is rare, or for example, very common, depending on situation, the commonality of that event should actually have a role in, what the classifier will tell you. Let me give you one example, which is kind of relatable. Imagine a patient wants to have a test to see if he or she has a disease, right? And the event is no disease. Now, the doctor tells the patient that they're going to be using a classifier or, kind of a test, which is a classifier, whose sensitivity is 90%. Now, you might think at first that sensitivity of 90% is good, is a pretty high number, is pretty accurate. But because these are conditional measures, that actually is not going to give you the full picture. Because when it tells you the sensitivity is 90%, what does that mean? That means assuming you don't have the disease, assuming you belong to the class of positives or events, I will tell you that with 90% accuracy. But that's assuming you do not have the disease. It doesn't look into the likelihood that you might actually have the disease. So depending on whether the disease is rare or not rare, that um, You might feel differently about a classifier like this. So, in order to kind of consider the prevalence, what we refer to for class positive and class negative, we define new metrics that are known as PPV and NPV, positive predicted value, negative predicted value. These are kind of similar to the concept of true positive rate, true negative rate, except for the fact that we look at the prevalence of the positive class when incorporated into this model. The idea is pretty nice because it kind of takes into account whether the class positive, which is event, whether it's rare or not rare. But in practice, PPV and NPV are not used that often because determining prevalence of a class is really not easy. A lot of times we don't have that information. A lot of times that information changes dynamically. For example, imagine COVID during the course of first few months since COVID started, prevalence would change. So it's not a static number. Sometimes it's not a static number, and in addition, it changes based on locality, based on different geographical regions. So typically, we don't have a good sense of what prevalence of class positive is. Hence, we don't use PPV and NPV that often in practice. But if you do have that information, you can use it in these two metrics to make it non-conditional. Now, a very common tool that we use in order to combine sensitivity and specificity into one map is known as ROC, or Receiver Operating Characteristics. Like many things else in data science, this name actually did not originate from data science. This came from communication engineering when they wanted to see, for example, a radar can detect an object, hence receiver operating characteristics. But essentially, what it does is it tries to give you a visual tool where you can see both sensitivity and specificity at the same time. And what it does is it looks at true positive rate, which is sensitivity, versus false positive rate, which is one minus specificity. Remember that sensitivity is true positive divided by total positives. Specificity is true negative divided by total negatives. False positive rate is false positives divided by total negatives, which you can think of it as 1 minus true negatives divided by total negatives. This is specificity. So that's 1 minus specificity. Now, let's think about it. Imagine you have a perfect model, a model that detects every event and every non-event correctly. This model is going to have a sensitivity of 100% and specificity of 100% or 1. Think of it like that. So if specificity is 1, that means false positive rate is 0. No data instance is incorrectly identified as positive. So in that case, sensitivity is 1, false positive rate is 0. On the other hand, imagine you have a random model. A random model basically is a new data instance comes in, you toss a coin. If it's heads, you say this is positive. If it's tail, you say this is negative. So it doesn't really do anything. It's not an informative model. In a situation like this, it doesn't really matter what threshold you have. Your true positive rate is always going to be equal to your false positive rate because you're tossing a coin, assuming the coin is fair, both of them are going to be equal. So when I look at it, the random model is going to give me always, regardless of threshold, is going to give me true positive rate the same as false positive rate. So x-axis is false positive rate, which in fact is 1 minus specificity, and y-axis is true positive rate. For a random model, both of them are equal, so this red line represents a random model. What about a perfect model? A perfect model is a model that gives me 100% sensitivity, 100% specificity. So specificity is 100% or 1. That means false positive rate is going to be 0. So perfect model is going to be sensitivity of 1 and false positive rate of 0. Now, what you do is you develop a model, develop a classifier, and then assign a threshold to detect events or non-events. Again, what is the threshold? Let's say in the spam email example, let's say if it's one typo, identified as spam. If it's 10 typos, if it's 20 typos, so that 1, 10, 20, those are going to be the thresholds to identify events versus non-events. Imagine in an example of classifying individuals as creditworthy or not creditworthy. In that situation, your threshold would be probably your credit score, right? So you say credit score below 600, not creditworthy. Credit score below 700, not creditworthy. Below 800, whatever. So that's 600, 700, 800, that's going to be your threshold. So what you do is you change these thresholds, and for each threshold, you test all the data instances. How many of them are correctly identified as positive? How many of them are incorrectly identified as positive? What are the true positives and false positives? And then what you do is you identify that ratio for each of the thresholds. What you get is this blue line. The more you move away from the random model towards the perfect model, that means you have a better model. So imagine this is one classifier, and imagine somebody else says, the new classifier that I have defined based on various threshold is this guy. This guy obviously is closer to the perfect model, so it's going to be a better model compared to that blue classifier that I showed you. This is what ROC does. Let's take a look at an example, a very easy example, and see how we would create that confusion matrix. A lot of companies that offer a product, they're interested in what is known as churn rate. That's the percentage of customers who leave that company or stop subscribing to a service. For example, companies, especially like, Dish Network, DirecTV, Comcast, they're very, very interested in making sure that churn rate is low so that if you're their customer this year, you're going to remain their customer next. Now imagine this company has a logic classifier that predicts the score for churn. You have 5 customers here, customer 1 through 5, and you basically assign a score whether that person is going to churn, meaning that leave the company, or not churn. These are the scores. And imagine I have ground truth as well. So I know, for example, that this customer will in fact churn, and the predicted score is 0.72. This person will not churn, and the predicted score is 0.56. Now, let's say for this classifier, you want to choose a threshold of 0.5, and you say, okay, this classifier is going to give me those numbers, those thresholds, those scores. And if the score is higher than 0.5, I'm going to identify the person as a churner. If it's lower than 0.5, as a non-churner. So what does that mean? That means this guy is going to be identified with a threshold of 0.5. This guy is going to identify as a churner, and in reality, he or she is. So that's correct. That's a positive. Imagine event is this person will churn. Event is positive, so that's true positive. This one will be identified as churner, whereas in reality is not a churner. So that's a false positive. Likewise, this one is going to be identified as a non-churner because the score is below 0.5, but the person will in fact churn, so that's a false negative. And these two guys both have scores below 0.5. The model predicts them to be non-churners, and they are in fact non-churners, so those are true negatives. So what I can do is I can look at my confusion matrix, and I can see that, notice I have 1 and 2 churners, and then 1, 2, and 3 non-churners. So I have 2 positives and 3 negatives. Out of the 2 positives, one of them is correctly identified as a churner, one of them is incorrectly identified as a non-churner. For the negatives, people who will not churn, 2 of them are correctly identified. These are true negatives. One of them is falsely identified as a churner, so that's a false positive. So then if I want to identify some of the metrics that I showed you in the previous slide, classification accuracy is going to be out of this total of 5, how many of them are classified correctly, which is 1, 2, 3. So 3 out of 5. Obviously, the opposite of that would be classification error. So 40% are misclassified. Sensitivity, true positives divided by total positives. Total positives is 2. One of them is correctly identified. as positive, so 50% sensitivity. And then specificity is going to be two of them correctly identified as non-events out of a total of three. That's based on a threshold of zero point 0.5. Now you can do this as an exercise yourself. You can change the threshold for that example to see how the sensitivity and specificity will change based on different thresholds. You can choose Turner threshold to be zero point 0.7, zero point 0.3, and see what happens. If you do have any questions, just feel free to unmute yourself and jump in. Now, what I showed you for the confusion matrix was a two-class example. You have a class of positives and negatives. In reality, you can implement this for a multi-class situation as well. In this case, let's say you have actual classes A through F, and you have predicted classes A through F, and you want to know how many of them are correctly identified. Diagonal elements of this matrix are correct identifications. Actual class is A, identified as A. Actual class is B, identified as B, and so on. Off-diagonal elements indicate misclassification. Oftentimes, but not always, oftentimes we try to label classes in such a way that the classes that are closer to one another are more similar. So for example, we try to label classes in such a way that B is closer to A than C is similar to A. So if, for example, a data instance belonging to class A is identified as B, that's an error, but that's a smaller error compared to, for example, the data instance being classified as C. If that's the case, and again, I emphasize, it's not the case every time, but if that situation holds true, then having elements farther away from the diagonal of that matrix indicates bigger or more severe mistakes. So here, for example, you have true class being C, but have been identified, five of them have been identified as F. Because F is 3 levels away from C, that's a significant error. So if you do have that order for labeling, you can look at the distance from the diagonal of the matrix to indicate how good or how bad um, this particular classifier is. Another interesting visual measure that we have is known as CAP, or cumulative accuracy profile. Again, this comes with a lot of different names: cumulative gains chart, Lorentz curve, power curve. Different domains have had their own names, but all of them mean the same thing. The idea behind this is very interesting. What you do is you sort your population. Imagine you have a classifier that assigns a score to every data instance. So you sort those scores from the lowest to the highest. Ideally, what do you expect from a classifier? You expect from a classifier that it assigns higher scores to events, to positive class, and lower scores to non-events, to negative class. So for example, if it's trying to assign a score, which is the probability likelihood of you being a churner with a service, or you being creditworthy, or you being anything really, you would like those numbers. If you are a churner, you would expect that score to be higher. If you are creditworthy, you expect that score to be higher. On the other hand, if the score is low, you would like it to really indicate that, for example, you're not a churner, or that customer is not creditworthy. For example, if you have a classifier, let's say, that assigns a score and says, hey, this customer has a score of 99%, but it just so happens that that customer is not creditworthy, that's a bad classifier. On the other hand, if a classifier says the probability for this person being a good creditworthy customer is only 5%, and that person really is not creditworthy, that's a good classifier. So that's kind of what we expect from a classifier that assigns those probabilities. So what I do is I sort those scores from the lowest to the highest. Ideally, what do I expect? Ideally, I expect that the ones that have lower score, all of them are non-events. The ones that have higher scores, all of them are events. So in a perfect model, hypothetically, let's say you have 10% of these data instances being non-events. Ideally, if you sort the scores, you would expect all the 10% that are non-events appear in the first 10% of the scores, the lowest 10% of the scores, or the first decile. So the first decile is going to be having all the non-events, and then the other, deciles are going to have pretty much, events or class positives. So what I do is I plot the percentage of non-events against the percentage of sorted population. In that example, the first 10% of the scores basically includes the entire 100% of non-events. And if you look at other deciles, there is no additional non-events anymore. This is a perfect model. What about a random model? A random model, again, imagine a data instance comes in, you toss a coin. If it's head, you say class positive. If it's tail, you say class negative. How many of you, let's say you look at the first 10% of your population. How many of them are non-events? It's a random model. So 10% of non-events happen to be in the first 10% of the scores. 20% of the non-events happen to be in the first 20% of the scores because there is no rhyme or reason to this classifier. 30% of the non-events occur in the first 30% of the scores. So essentially, the relationship between percentage of non-events and percentage of sorted population is going to be a straight line, the red line that I'm showing here as random model. Again, like before, like the ROC, the closer you are to the perfect model, to this green curve, that means the better model, the more improved model you are. So this blue model is going to be improved compared to the random model. Let's look at this through an example so it makes better sense. Imagine I have a classifier. I'm going to call this classifier A that assigns scores to individuals based on how creditworthy or not creditworthy they are. So the event of interest in this case is the person is creditworthy. And ideally, like higher scores to indicate creditworthy and lower scores to indicate not creditworthy. Now, let's say I have done this for 20 individuals. So my model, my classifier, let's say a logic classifier, has assigned a score for these 20 customers or 20 individuals. Imagine I have ground truth as well. So I know in reality if these people are creditworthy or not creditworthy. Now, take a look at some of these numbers. Notice that some of the people who are not creditworthy actually have very high scores. So for example, this guy is not creditworthy, but the score that the model gives to him is 78. For this person is 77, which is a high number. For this person, 83, which is even higher, or 71, which is high. That tells me that this classifier is not really perfect because it is misassigning higher numbers to individuals who are otherwise not creditworthy. Let's do the cap for this classifier. So now that I have the scores and individuals' ground truth of whether they are creditworthy or not, what I can do is I can sort them. So I sort those individuals from the lowest score of 35 to a highest score of 93. In an ideal situation, if this classifier was perfect, what would I have expected to see? All these low values would be not creditworthy. All these high values would be creditworthy. Take a look though. You see here that there is one individual with a low score which actually is creditworthy, one individual with another low score which is creditworthy. That tells you that this is not a perfect classifier, but let's see what CAP gives us. So what I do is I look at the individual deciles. This I had 20 customers, so a decile is going to be 2 customers. And I count how many non-events I have in each decile, and essentially what the cumulative percentage is. Let's take a look here. Here, first of all, I have 1, 2, 3, 4, 5, 6, 7, 8 non-events. So totally, I have 8 non-events, which is my 100% of non-events. Let's take a look at the first decile. In the first decile, which is the first 2 observations, both of them are non-events, which is great. Two out of the total of eight. So 25% of non-events occur in decile one. So in decile one, I have two non-events, which is 25% of total non-events. Let's go to decile two. So these four. These four, I would hope that all of them are non-events. So I would hope that, 50%, four out of eight, 50% of non-events happen to be in decile number two. In reality, however, only three non-events occur here. So three out of total of eight, because one of them is event. So in decile two, I have 37.5%. What about decile three? What about decile three? Decile three would be these six guys. And in these six guys, I have one, two, three, four non-events out of a total of eight. So that would be 50%. And I continue this. So I sort the population and I say in um, this again is the red line is my random model, the green line is my perfect model, and I say for my model, which I show it in blue, in the first decile, I have 25% of non-events. In the second decile, I have 37.5. In the third decile, I have 50%, and so on. And then I connect everything together all the way when I go to 100%. You notice that this cap line for classifier A is moving up away from random model towards the perfect model. So that means obviously it's a better model than random model, but it's still kind of farther away. What I can do is I can further improve it. Let's say I have another classifier, classifier B, which offers scores that for non-events or not creditworthy individuals actually are lower, which is more ideal for me. So this person, which before was like 70 something with classifier A, classifier B assigns 65 to it. This guy again was 77 or whatever. This classifier assigns 58. This classifier assigns 60 and 40 to these other two guys as well. So you would expect that this classifier would be a better classifier compared to the first one. Let's see if CAP does the same thing. When I repeat the analysis, I can see, let's take a look at it here. Actually, I don't have the sorted data, so that doesn't help. But anyway, I have done this analysis before, and what you see is that in decile one, two, three, you have 25%, 50%, 75% of your non-events. Let's compare with the previous one, 25%, 37.5, and 50%. When I connect these dots together, I can see that classifier B becomes this line. Notice how it's how closer it is to the perfect model. So it's a better model compared to the random model. So this cap kind of gives you a visual tool to assess how much better one model, one classifier is compared to another classifier. Sometimes, however, instead of just looking at it visually, you would like to have a number. One of the numbers that we use is known as accuracy ratio. Accuracy ratio basically looks at area under the model you're considering minus area under the random model divided by the area under the perfect model minus area by area of the random model. Kind of something like this. Imagine this is your perfect model, this is your random model, this is your model that you have developed. So area under the model minus area under the random model, this is this area divided by area under the perfect model minus area under the random model. So it's going to be this whole area. You divide this area by this area, and that's going to be the accuracy ratio. For perfect model, obviously, accuracy ratio is going to be 100%. For a random model, it's going to be 0. The last one we're going to talk about, another metric, is known as lift. We call it lift because it kind of is a measure of how much the model lifts non-events over the random model. And a lot of software packages actually derive these for you. So plot, the cap curve or the lift curve for you. But in case you want to do it manually, it's not that difficult. Essentially, again, like I said, imagine you have a random model. 10% of non-events occur in the first 10% of data. 20% of non-events occur in the first 20% of data. 30% non-events, first 30% of the data. So, that logic. What we do for the random model is for each of the deciles, we count the number of non-events divided by the decile itself. So a random model in the first decile offers 10% of the non-events. We divide it by the decile 10%, we get 1. In decile number 2, it has 20% of non-events. We divide it by 20%, it gives me 1. So we repeat this, and for random model, lift is going to be just a straight line of 1. Now, if, for example, let's say a particular model in the first two deciles, so decile number 2, 40% of non-events are included there, the lift value is going to be 40% included in the first two deciles, divided by what the random model would have given you, which is 20%. So that would be 2. So the lift value is 2. The farther away you are from that straight line representing the random model, the better model you have. What I did was I did the analysis for classifier A and B. And again, you notice that classifier A is better than random model, but classifier B is better than classifier A because it's farther away. It's kind of lifting, quote unquote, non-events over the random model. So these are different things you can do to assess, to compare the performances of two different types of classifiers. Now, the last thing we're going to talk about before we stop for today is the problem of class imbalance. This is a significant issue that we have in a lot of different classification problems. Ideally, you would like, when I say ideally, I mean from a mathematical perspective, you would like to have an equal distribution of events and non-events. In practice, though, this is not the case. In a lot of times, the event of interest is not very common. For example, in an insurance company, they may have hundreds of thousands of customers, but only a very, very small percentage of those customers will file a claim. So if I consider event to be the person filing a claim versus not filing a claim, this is a very, very imbalanced situation. People who click on an ad, people who, order a specific service, a specific product, people who have a specific disease that may not be common. In all these situations, you have one class which is very rare, which has very low number of data instances, and one class which is very dominant. In this situation, if you train the model, what's going to happen is if you don't pay attention to class imbalance, you're going to end up with a model which has good specificity, meaning that it mostly identifies individuals or data instances as non-event, as negative, because majority of them are anyway. Imagine you have a situation in which you're in a population of 1,000 people, only 2 people have a certain disease, right? If I have a classifier that really does nothing, any data instance that comes in, it says this person doesn't have the disease. This data set, this classifier is going to have a very high specificity because pretty much every majority of data instances that are non-events, which in this case is most of the data instances, are correctly identified as such. But this is done at the expense of incorrectly identifying the people who have the disease because that's a minority class. So these models typically, in these classifiers trained on these models, typically have good specificity but very poor sensitivity, which is problematic. So in a lot of models, if you have class imbalance, you have to put a lot more focus on the sensitivity for the minority class. So make sure that people in the minority class are correctly classified. There are different ways we can do this. Um, one for instance, one way is to sample the two data, the two classes. Imagine the diagram on the left. I have my original data. I have a minority class, everybody in class blue, and then I have a majority class. As you can imagine, you have more data instances in the majority class. If I just randomly take a sample of this data set and feed it to my classifier, chances are it's going to be specific but not very sensitive. What are the things I can do? I can either downsample or upsample. Downsample means you sample properly from the minority class here, but when you want to sample from majority class, you downsample. You take fewer samples from the majority class so that there is a little bit of a kind of a connection between the two. Another approach is upsampling, meaning that you sample, let's say 30%, 40% of your majority class, but then from minority class, if I do 30, 40%, I'm not going to be left with that many data instances. In that situation, I take multiple samples, so sampling with replacement, so that I have more representatives from the minority class. And this way, the two sets can become more comparable. Other things that you can do is you can, for example, when training the model, make sure you give higher weight to sensitivity. So you penalize for poor sensitivity. You don't give too much priority to specificity. That's one way to do it. Or sometimes what you can do is you can kind of play with the threshold to see if there is a situation that your sensitivity, if there is a threshold for which sensitivity can be improved without impacting specificity that much. These are the two things that we can do during, tuning and training of the model. So that kind of brings me to the end of this lecture. We kind of finished early. But so what have we talked about so far when it comes to classification? We looked at the fact that in classification, we have to do feature selection because not every feature, not every dimension is relevant to the class label. We looked at a series of important and common classifiers, probabilistic models, k-nearest neighbors models, and also performance metrics. So this kind of wraps up the discussion on classification. Like I said, we will be talking about tree models hopefully next week, which is yet another classifier. But I'm not necessarily lumping them under the title of classifiers because they do other things as well. Now you should be ready to do the second part of course project two. I'm assuming many of you have already started with the clustering approach, but the second part, which is classification, now you have all the tools to get started on that as well. All right, let me stop recording.